All right, let's take a look at amines. Amines have this formula where we have a nitrogen with some number of alkyl or aromatic groups attached to it. These groups can be tied back into rings, or they can be just simple alkyl groups. If there's a simple set of alkyl groups, such as in the case of adrenaline here, then we call that an aliphatic amine. If the nitrogen is within a ring, then we call it a heterocyclic amine. And if the nitrogen of the amine is within a aromatic system, they call that an aromatic amine. Now, there's many famous or well-known amines. Aniline is a simple aromatic amine. Nicotine is the biologically active component of cigarettes that's incredibly of tobacco that's incredibly addictive. Codeine is a very potent anti-pain medication. Adrenaline is produced by your body in that flight or fight response. And then there's many other amines that are common in biology labs. Pyridine, it's a very common base in many applications, so is triethylamine. Now, conine is a famous amine. It is one of the poisons of the hemlock plant, and it's said that Socrates was forced to his death by drinking poison from the hemlock, and so it would have been conine that caused his death. Now, we can classify amines as either primary, secondary, or tertiary, and that classification is a bit different to how we classify alcohols. In an alcohol, because the oxygen must have one alkyl group and one hydrogen, the only choice is whether the carbon attached to the oxygen has 1, 2, or 3 substituents. Whereas with nitrogens, we can have an amine that has either 1, 2, or 3 carbon substituents on the nitrogen itself. And all of those are amine functional groups. And so if we have one R group or one carbon substituent and 2 hydrogens on the nitrogen, then we call that a primary amine. If we have 2 carbon-based substituents and 1 hydrogen, that is a secondary amine. And if we have 3 carbon substituents and no hydrogen attached to the nitrogen, then that's a tertiary amine. There's also the possibility to have a 4th substituent added to the nitrogen. So we get the nitrogen lone pair of electrons and we make it react with an electrophile. So we now have an extra nitrogen carbon bond, and the nitrogen now has a formal positive charge. And that we call a quaternary ammonium salt or a quaternary ammonium ion if we're just looking at the nitrogen part. And so, for example, this, which should be named tetraethyl ammonium iodide, is an example of a quaternary ammonium salt. The naming of amines is really most commonly done the same as with alcohols. So this would be 3-pentanamine, this would be 1,3-propyl diamine, and this would be cyclohexylamine. However, in many instances, we actually name these compounds as an amino substituted compound of some type. And so this compound here is 4-amino-2-butene. This compound is 3-amino-1-propanol, and this compound here is 2-amino-propanoic acid. There's many amines that have common names, and many of these are historically well known. So putrescine and cadaverine, as the name suggests, they're both produced by decomposing organisms. And so particularly cadavers and roadkill and things like that, their foul smell will be largely linked to molecules such as these diamines, putrescine and cadaverine. The nomenclature of some compounds, it's important to note that if there's a group attached to the nitrogen, sometimes we want to name that substituent in a way that tells us it's on the nitrogen and not somewhere else on the molecule. So this 6-membered nitrogen heterocycle is commonly called piperidine or piperidine, and if we put a substituent on the nitrogen, we want to say that it's on the nitrogen by putting an italicized N in front of the alkyl group. So this is N-methyl piperidine. And that tells us it's different to 2-methylpiperidine, which gets its name by numbering 1 where the nitrogen is and 2 is the next position around the ring. We could also name this molecule 1-methylpiperidine, and you'll see that that's actually more commonly used in some circumstances, but often we name it as the N-substituted compound instead. So this compound here would be N-diethylbutanamine, which is different to N-ethyl-2-ethylbutanamine, which is different to 4-ethyl-3-hexanamine, which is this compound here. Probably the most important thing to note about amines is that they're basic, they're weak bases. They can pull a proton off stronger acids. If the acid is just something like water, which is a weak acid, then the equilibrium lies over towards the starting material. So the amine is not strong enough to pull off many of the protons of water. So we have only a small amount of the ammonium ion in solution. Now, having said that, aliphatic amines like this are more basic than aromatic amines, particularly anilines. So when we have the nitrogen attached to a benzene ring, we can draw resonance contributors to this overall structure where we push the pair of electrons, the lone pair of electrons, in to make a new pi bond here, and push this pair of electrons out onto this position on the benzene ring. And we can draw a series of resonance structures where that lone pair of electrons has moved on to the benzene ring. Now, each one of these contributes somewhat to the overall structure of aniline, and we know that resonance contributors make the overall structure more stable. Now, those resonance contributors for aniline itself, there's no analogous contributors to the protonated aniline. So if we take this lone pair of electrons and react it with a proton, it's no longer available. That lone pair of electrons is no longer available to form these resonance contributors, and so the aniline, the conjugate base, benefits from resonance, whereas the conjugate acid, the protonated aniline, does not, and so therefore it prefers to stay as the non-protonated conjugate base than as the protonated form, the conjugate acid. So amines are basic and they can react with acids such as hydrochloric acid to make ammonium salts. So that's an example of their Brunstead basicity. I wouldn't really generally call that an example of their Lewis basicity, although there's overlap of the definitions of Lewis and Brunstead acidity and basicity. However, amines can also act as Lewis bases by donating their pair of electrons to a Lewis acid and form adducts in that way. They can also act as nucleophiles, so they can react with things like alkyl halides to form ammonium salts. So here's a secondary amine reacting with its pair of electrons as a nucleophile to form a new bond to a carbon atom here and displacing a leaving group, which is a halide, to form a trialkyl ammonium salt. There's many ways to make amines. One of the more common and historically one of the oldest ways to make amines is to take a nitro compound and reduce it. So if we reduce it with a hydrogenation in the presence of a catalyst, we call that catalytic hydrogenation. Or an older method is to treat it with tin, metal, and a mineral acid such as hydrochloric acid. So here we've got a aromatic nitro compound. We treat it with hydrogen and a palladium catalyst, and we generate the amine. Amines are also formed as a byproduct of protein degradation, and so that's why we get these smells when living organisms die and then their bodies decompose. It's many of these volatile amines being produced. And so here we've got an example of decomposing fish and some litmus paper that's being turned a color by the basic amines that are being produced during the decomposition. Alright, so hopefully that gives you a little bit of background about amines, their structure, their reactivity, and some important points about their properties. Thanks for watching.